The aim of this problem is to help students to refresh their memories regarding solving a differential equation using Laplace and Laplace inverse transform and using partial fraction expansion. To solve this problem, we need to look at the Laplace transform and the Laplace inverse transform, and we also need to use transforms of the derivatives. Based on the transform of the derivative, we know that the first derivative Laplace transform of the first derivative is SL f of t minus f0. Second derivative is s square L f of t minus s f0 minus f prime 0, which f0 and f prime 0 are initial condition, first and second initial conditions. And then after transforming to the Laplace transform, finding the transfer function of this differential equation and the given input, we need to use the partial fraction expansion in order to solve to find the components of the response, and then we need to use the Laplace inverse to solve the to find the time response of the system. In order to use the partial fraction expansion, again from your control module lecture notes, you can find the different examples and way of the solution. So for a rational form of the Laplace transform, which given here such as the GS, we need to first to find the poles of the transfer function, which poles are defined as the roots of the denominator. Based on the type of the roots, depends if we have the complex conjugate roots, or we have the simple real roots, or we have repeated roots, we have different actions to take. For example, if we have the poles all simple and real, then we can factorize the transfer function g of s as q s over s plus s1 to multiply to s plus sn, and then we can separate the components or each pole as shown here. What we need to find the constant ks1, ks2 to ksn. How we can find it? To find this coefficient, we need to follow this methodology. KSI is the limit of function s plus si multiplied to qs over ps or g of s when s goes to si or s goes to minus si. The value of this or limit of this function will give you related KSI. If we have the complex conjugate poles, we need to follow the same methodology. However, it is a little more complicated because of the complex form of the poles. So if again you look at the lecture notes, you will find how we can solve the partial fraction for the system with the complex conjugate roots. So I recommend to the students, to review their lecture notes from control module in order to refresh themselves how to solve differential equations using Laplace transform, Laplace inverse transform, and partial fraction technique. To solve in part B of the problem, it has been asked to solve this differential equation using MATLAB. The main part of solving part B is to use command residue. Command residue help you to find the coefficient of a partial fraction expansion. To use the MATLAB to help yourself how to work with the command residue, if or any other commands in MATLAB, you need to use the command help. For example, I want to know how to use the command help to use the command residue. If I type in the MATLAB window help residue, the MATLAB will give me all information how to use command residue. For example, command residue has the three outputs. It has two inputs. The b and a are the numerator and denominator of the transfer function. R, E are the residues. P E is the vector of the poles, and K is the vector of constants, is any available. So I recommend you to use the command residue to find the partial fraction for this, for the Laplace transform of this differential equation, and again using the Laplace inverse find the YT, or response of the system.